I'm going to actually move all those chairs out of here because that was like for a panel or something that happened earlier, and I just didn't notice that they hadn't yet moved. So, but if everybody can find a seat, we'll get started in just a minute or two.
Howdy, howdy.
All right, folks. Welcome to Chadev. Some of you who are here often, some of you who are not here so often. We welcome you. Happy you're here. Today we're hearing from Tom Richards. This is one of the second or third talk in our new sort of format of trying to help all of our community create better, more engaging talks. So definitely judge Tom really hard if it sucks, because no, actually it's all our fault because we were trying to help him. So anyway, we're really excited about this. We hope that you all are excited about it. We hope you all are inspired to speak. If you do have something that you're interested in speaking about, please reach out to one of the organizers, myself, John, Justin. We'd love to get you sort of on the schedule and part of the process. So with that, I'm going to turn it over to Tom, and looking forward to hear what he has to say.
Thank you, thank you. Everyone hear me all right? Yes. Excellent, great. Okay, so we'll jump right in because we got a lot to cover. Start off with a tiny bit of housekeeping. I know that here at Chadev we've seen presentations in the past about things like asset building tools, right? You know, Webpack and Brunch and Gulp. And I know that we're all tired about hearing about those things, so we're not going to talk about them exactly, but we are going to talk about optimizing for the smallest file size. So in the grand scheme of building assets, you have asset building tools, and they do the following three things. They take your source files, and they mangle them a little bit, and then they mangle them a little bit more, and then finally they produce a set of static assets. So today what we're going to talk about is mostly number two there, right? We're going to optimize, compress, shrink down those files. Stuff going on under the hood of your asset building tool. And before we talk about the fun file type stuff, I think it's important to ask a few questions first. So why do this, right? Why bother shrinking files down? There's a bunch of good reasons to do this. And I think it applies whether or not you're making stuff for the web, or maybe you're making stuff for mobile or even desktop. Chances are the stuff that you're making is going to get transferred over the internet somewhere, right? The reasons you want files to be small and your transfers to be efficient is for reasons that you already know. So first and foremost, you want to save time, right? When you've got smaller files, this means they transfer over the network faster. When you've got smaller files, this means they transfer to and from your storage device faster. Save time, have small files. Some people have bandwidth caps, right? Think about people that have bandwidth caps on their mobile data plans, people that have bandwidth caps on their home internet service provider, right? Think about the users that are downloading your stuff and how much they'll appreciate it if you're not eating into their bandwidth cap for the month. Transferring stuff over the network usually costs you money, right? So many cloud services nowadays, you're using AWS or Google Cloud, right? You're being billed by the pay for what you use billing scheme, right? Unless you've got unmetered bandwidth, transferring stuff out is going to cost you money, right? Maybe it doesn't cost you anything. Maybe you're super cool. You've got unmetered bandwidth or whatever. But someone, somewhere down the line is paying for that, right? There's no such thing as a free lunch. I would highly recommend checking out the whatismysitecost.com site, because the pay for what you use billing scheme, it can also apply to mobile internet users as well, right? So if you are downloading a quote unquote lightweight page, right, the Reddit front page, for example, this thing weighs in at just over a meg. And according to this site, if you're using a mobile ISP in Canada, sorry about the quality there, not sure what happened, you might be charged as much as 13 cents to see that site. So, you know, think about users with high-cost mobile data plans. Okay, so time and money is important, but what about disk space, right? If you've got an SSD, we know that SSDs are lovely, right? They're fast, but they're generally smaller than their spinning platter counterparts, right? So save space on your storage by shrinking your files down. Okay, final reason. We know that hard drives and solid-state drives both fail, but they fail kind of differently, right? So solid-state drives, they've got a limited number of writes that they can withstand before they kind of die out. So you want to increase the lifespan of your SSD, shrink your files down. That makes it where you perform less writes on the storage, increasing the lifespan of your device. Okay, so those reasons out of the way, we want to talk about some things that we should do before we even attempt to optimize files, right? So there's some stuff that are mistakes that we can make. There's junk that we should eliminate before we even try to optimize anything. And this is where we're going to see the most significant savings is just by getting rid of junk that we have. So a couple of examples of junk that I see a lot is images, right? If you've got an unnecessarily large image on your page, it can be one of two problems mainly. Like you've got an image that's too big or you've got an image in the wrong format. And we'll talk about this a bit more later, but a kind of key takeaway here is to use the right file type for the job. So just taking an example here, this home page here, we've got some lovely images, and they're pretty and all, but the thing that you won't notice until you really dig in is that these images are just wrong, right? This guy is a format of a ping, and it's a super humongous image, and that's just not right? We don't need to use a massive image where a smaller one's gonna do, and we don't need to use a ping where a JPEG is gonna do. Right, so ping is superior for some reasons we'll talk about later, but I think this pretty much covers it. Okay, another mistake that I see often in terms of bloated stuff is ads, right? So I'm not talking about all ads. Look, I get it. I work for a marketing agency, and we definitely support the advertising model, but if you've got a particularly crummy ad network, you'll tend to find that those bring along a lot of bloated, unnecessary, third-party scripts, and you can end up with a page that looks something like this, right? So I think we can all agree that what's going on here is just absolutely preposterous, right? This thing, look at it going. It's generating a redirect chain of like hundreds of layers deep, and it's really not downloading an enormous amount of data, right? We're only at like 1 meg, but I bet if you left this going, it would really eat things up, right? It eats up your battery, your CPU cycles, your data plan. This is disgusting. Please don't do this. Yeah, so the solution for all of those bloaty things is just delete it, right? Now I understand that we can't just delete everything always, so we want to talk about just kind of some generic strategies for optimizing the stuff that we do have. And there's a few simple things that we can do to help out, and if there's anything you take away from this talk, it should be the next 3 slides. Okay, so here we go. 3 generic rules for optimizing anything. First and foremost, use the right file type for the right job, right? The example we showed earlier, we had a massive ping. Instead, what we should have had was a nice compressed JPEG. So it's important to know what the right file type is for your situation and use it. And we're going to cover a bunch of different file types later, so we'll ask the question about what is the right file type and how do we choose it. Optimizing the right time. So I've seen a lot of workflows where people will, they've got these images, right, and they're running them through these asset building tools, and they're just blindly running it over and over and over again every time they run a build. All right, so why waste time optimizing things twice, right, when you could just optimize your stuff once ahead of time before the user sees it, before the user asks for it. That's the correct time to optimize. And finally, optimizing for churn. So when we're sending files to our users, we want to make sure that we're not re-delivering the same old files, and the old files are masquerading as new ones, right? So that's what we call churn. If a user has visited your site before or used your app before, chances are they've already got some assets in their cache, right? They've already got some versions of the downloaded stuff from previous, and don't make them download it again, right? That's churn. All right, we said the 3 rules, and you can stop listening, talk over. No, but seriously, we're almost at the last question, then we can get to the fun stuff. So how much do we want to optimize things, right? We have a bunch of tools and workflows at our disposal, and the stuff that we want to try to aim for is the low effort, high reward type of solutions, right? So maybe they won't all yield you 80% savings. This graph is made up. But the point is that the stuff that you want to try to use is low effort and provide at least some amount of shrinking. Final question. Not just what kind of things can we optimize, but what kind of things do you want to optimize? I would argue that the answer to both of those questions is you should want to optimize all of the things. Okay, fun stuff. So for the rest of this talk, what I'd like to do is kind of give the whirlwind tour of file types and how to shrink them down. So for each file type, what we're going to do, we're going to cover what the file type is, where it's useful, what kind of tools you can use to shrink it down, and then for a couple of them, we can talk about the internals that allows us to shrink them down. So there's a bunch of stuff here, and we're going to start with the boring ones that we can just kind of breeze through here. You guys already know about these, right? There's nothing particularly interesting about plain text files, right? The internals is just, it's plain text. You can just kind of open it up and look at it. CSS is our first example, right? Cascading style sheets. This is the stuff that gives you style on your websites. There's at least a couple of popular tools out there. So this is the GitHub username and GitHub project name for each of these tools. Just to give a quick example of what that looks like, here's the CSS file. We've got kind of some duplicated selectors at the top and bottom of our file. And once we run it through one of those tools that we just put on the slide earlier, we got a 16% savings there automatically, right? So this has been minified with the CSSO optimizer tool. And what it's done is it's done some structural optimizations. It's gotten rid of white space. It's combined some of those duplicate selectors that we had. So, you know, not super great savings, but something anyway. Okay, ECMAScript, my absolute favorite programming language of all time. You know, we can't say the word JavaScript anymore because Oracle will write you a big nasty letter if you use it without their permission, right? I will try not to say that word, but you know, just in case it slips out, sorry. So if you are using the old version of ECMAScript, you probably want to use this tool up here at the top, Uglify.js. If you've got a fancy new ECMAScript, you know, ES6 and above, you might be able to use the Babel tool because it's newer, but it is still kind of beta, so you know, your mileage may vary there. Short example of some ECMAScript code, we've got some brief code that's doing a trivial calculation, and when we minify it, we get some pretty significant savings there, 39% savings running it through Uglify.js 2. We've eliminated comments and white space and dead code and a whole bunch of other stuff. If we had fancy new ECMAScript, we could potentially run it through the Babel tool, which would do a thing called tree shaking. This is where it would eliminate unused modules, right? So like, say if you included a module like jQuery, it would eliminate that if you didn't use it anywhere. HTML, the hypertext markup language. This minifying HTML is really not as popular as minifying all the other things we talked about already, but it can be helpful if you've got lots of markup that you want to deliver, or maybe static HTML files. Here's a tool, and the default configuration for this one's kind of funny. It will remove what it thinks are unnecessary tags, and the things that it thinks are unnecessary tags are things like the head and the body, and I'm not totally certain that that's correct, but here's an example. We've got HTML, and it's a simple page, and running it through that tool with the same configuration where we told it not to get rid of the head and body, we've got 13% savings, right? So if we were to want to play with fire and try to get rid of those unnecessary like wrappers, the head and body, we could do that. I think that's maybe a little dangerous, but give it a shot. JSON, the JavaScript object notation. Said the word, didn't I? Okay, so are we gonna have to rename this to ESON since we can't say the J word anymore? Is that how it's gonna work? Okay, so in ECMAScript, the JSON stringify function spits out minified JSON by default. It's just built in. If you're using a module bundler already, chances are it's using that to print out minified JSON. And sometimes your ECMAScript minifier can do that as well. Just a brief example of JSON data. It's kind of dense by default because we've got curly braces and square brackets instead of like the big bulky XML tags. So we're going to get a pretty significant amount of savings by just removing white space. There's an example. After running it through JSON stringify, we get 44% savings. That's pretty significant. Okay, XML. So this is the extensible markup language with all the big bulky tags. The GNOME XML parser project, which you're probably using and don't know it, it's got a command line tool called XMLint, and XMLint will not only validate, but it will also format your XML as well as HTML. And like I said before, XML has these big bulky tags that make it kind of tough to minify. So once you've done the best that you can hope for, which is eliminating white space, you get 15% savings. Not a huge gain, but still something, especially when you're dealing with large amounts of XML data, which when are you not dealing with large amounts of XML data? All right, plain text files are over. This is the fun stuff here. We get to talk about binary files. When I'm talking about binary files, I'm talking about things like images, videos. So this one's tough. Image optimization is really not an exact science. It's as much of an art as it is a science, right? If you were to ask me, hey, I've got this specific image here, how do I optimize it? The answer to that question is almost always, well, you know, it depends. So we can just kind of run through a brief science and art checklist here. How do we optimize images? First thing we want to do is use a vector format, right? If we can, and this isn't always applicable, you should prefer to use a vector image over anything else. And the reason you should do this is because math, right? It's really super easy to represent a simple graphic or a drawing as a vector image, right? A set of like points and lines and polygons, and this makes it really easy to scale up because you want to resize the image. Okay, great. You just do the math again with bigger numbers, as opposed to a raster image over there on the right-hand side where you've got pixels in a grid. You want to upscale that. Sorry, you're stuck with those pixels for forever. And I think this one kind of goes without saying, but you know, compress your vector assets. There's tools for that. SVGO is one of them. This applies something like a dozen different optimizations to your vector file. It'll clean up empty attributes and remove hidden elements, so on and so forth. Definitely take a look at that if you're dealing with vectors. Next thing, so you can't use a vector all the time. You want to be sure that you are picking the right raster image format. How do you know? What's the format you should use, right? So if you've got a need for an animation, you are stuck with GIF. Sorry, that's the only format that supports animation consistently. Ping can kind of do that a little bit, but it's more suited for lossless compression, high resolution, fine detail, and it does also support the palette storage, kind of like GIF does, where you have the ability to store a limited set of colors if you want to store the image more efficiently. And then for everything else, you're probably going to use a JPEG image. This is a lossy image format that just kind of applies little distortions to the image that makes it compress better. So if there's a thing you take away from this slide, it's that the bitmap format is amazing because it's trivial, right? You know, you've got just like, here's the green value, here's the red value, here's the blue value, next pixel, right? It's super trivial to implement, but like it's really not a smart format. You should definitely prefer to use at least a lossless compression format. And if you're looking at a typical photograph, chances are you want a JPEG. When you want a JPEG, you should experiment with the quality setting. What you'll tend to find at the higher JPEG quality settings, and this is kind of weird to look at here, we've got the higher setting on the left-hand side, the lower setting on the right-hand side. The size of the JPEG file, we're comparing this to a compressed ping file that is. So when we've got quality 100 on our JPEG, we've actually lost reduction size, right? We have gone up almost by double by using 100 quality JPEG. Right, so don't be afraid to dial that down, especially like this gap right here. That's an important one. Right, so that's about like 90 quality setting. If you can aim for like 89 or maybe a little lower, you get about half savings, and yeah, don't be afraid to dial it down. Higher is not always better. So the quality setting in JPEG, this is kind of a funny thing. Most lossy formats, whether you're talking about images or videos or audio, they all pretty much use this technique called quantization. I'm going to give a super simplified and not 100% accurate description of what that is. So let's say that you've got a range of values, right? So like maybe they're the colors of pixels in your image. And if you want to compress these better, the thing that you need to do is you need to reduce the number of unique values that you've got. So what do? Well, you just kind of run it through this really rough rounding process, right? So the final numbers that you end up with after applying the rounding process are what you call your quantum values. So you've got the same number of values, but the point is that you have fewer distinct values. And this is important because that is the feature that allows it to be compressed more. Yeah, so the quantization thing, it turns out that there's a bunch of different optimal ways of storing those quantum values inside of your file, and there's just as many not so optimal ways of storing those values inside your file. There are tools that can help you maximize your savings in that area. Same thing goes for metadata, right? There's a bunch of tools that can help you optimize your savings for a bunch of unnecessary data inside your image, right? Things like where you took the photo and what make and model of camera you used and what software you used to edit the image, right? What are the tools that we can use to get rid of this stuff? Well, there's a bunch of them, right? And you know, Ping deserves half a slide over here because it has so many dang tools. Some of these are kind of new and you may need to compile from source to be able to use them. And they can be kind of complicated to use on the command line, so I would recommend just falling back on ImageOptim. This is an amazing tool. This is image optimizing easy mode, right? It's literally drag and drop, and it shows you how much savings you've got over there on the right-hand side. If you're not on Mac OS, there are alternatives for this tool that run on Windows and GNU Linux. If you just search for something like, Image Optim Linux, it'll get you there. OK, so video files. Video files are just images, but a lot more of them, right? You have many frames per second, and those are all just basically images. Once again, choosing the right type of container, choosing the right type of codec is absolutely critical, right? So maybe you're dealing with an old system, and you can only deal with animated GIFs. You're stuck with a big file, sorry. If you have support for modern codecs, though, you should definitely use those because they're way more efficient than a GIF should or could ever hope to be. Super brief, quick explanation about codecs and containers. Codecs are these things that we use to encode video. Over here on the left-hand side, we've got H.264. Those are video codecs, H.265. On the right-hand side, you've got audio codecs. At the top there, we've got just kind of like a plain text file, right, like subtitles. And all of those things get bundled up together in what we call a container. This particular one is MKV, or the Matroska format. So yeah, codecs encode the streams, containers contain the codecs. Here's some popular video codecs that we have and the years that they were released. So things like MPEG-2, right? We see this all the time in DVDs. If you pop a DVD into your DVD player, it is reading an MPEG-2 stream. It's not super efficient. Just about a decade later, we came out with what we call the H.264 Advanced Video Coding. Right, so what this is if we're looking at a particular video and we choose to compress it at the same visual quality using H.264, it's going to require half the number of bits, right, half the file size. And again, in 2013, we did the same half savings, right? So we came out with H.265, the high efficiency video coding, and what it did was allow us to keep the same quality of video, half the number of bits. Or if you wanted to keep the same number of bits, you could have a much better looking picture with fewer compression artifacts. So yeah, definitely prefer to use a high efficiency codec where you can, if you're making a DVD, sorry. So yeah, video coding is immensely complicated, and easy mode for this is Handbrake. This is a wrapper around FFmpeg. It's got all the quantization stuff from before, but it applies it to the thousands of video frames all at once, and there's a bunch of presets. Super great tool. I'd highly recommend looking at it. Audio files, right? People don't tend to have WAV players, right? You tend to have like an MP3 player. That's because it's a compressed format. The thing that you want to use is, once again, the right tool for the job, right? So there's some compressed formats, things like FLAC. FLAC stands for the Free Lossless Audio Codec, and it's kind of like the PNG of audio, right? When a FLAC file is decoded, it's 100% identical to the uncompressed file. So how do you use this to get the most savings? I've got an example of a song I'm downloading from Bandcamp here, and I think it's important to point out that the WAV file here, WAV is 47 megs. That's kind of big. If we are using the FLAC format, though, we've got 39% savings compared to the WAV. And another thing that I want to point out is Bandcamp's really smart here. They didn't use the default compression setting for FLAC. They've used the level 8 compression setting to compress FLAC, and that gives them the 39% savings. So this is cool, but we can also do better, right? We've got these other MP3 formats here, and I know that audiophiles out there are going to hate me for saying this, but MP3 is actually a great format, right? It's like the JPEG of audio. Instead of playing tricks on your eyes, it plays tricks on your ears, right? It adds a little minor audio distortions, which your ears shouldn't be able to hear. And there's some quality settings that you can use to make it where you are not able to hear those distortions, right? So if you want to, say, archive a file for future records, your recording studio, and you need absolute quality, don't use MP3, right? But if you are listening to a file on your mobile audio player, maybe you're listening to it on a noisy train, or you're listening to just a couple of voices like radio, definitely use a smaller file size. And the thing that you should use, I think, is the V0 format. So the reason that you want to use V0 format is because it's transparent. And what that means is if you've got an MP3 V0 file and you're comparing it to the complete uncompressed version of that audio track, you're not going to be able to tell the difference. I challenge you to be able to tell the difference. So just a quick comparison of what we're looking at in terms of savings between the different formats here. Once again, WAV is kind of trivial, right? It's not super smart, but it does encode the file. At the very least, you should be using a compressed FLAC type of format and use MP3 V0 over there on the right-hand side for 70% savings over FLAC. All right, PDFs. So this is the portable document format. You're looking at all types of documents that get produced in this area. There's some tools here that are included in the Tails operating system. So this is a set of tools that you can use to strip away PDF metadata, redact sensitive information. It's kind of rough around the edges if you've used it. It's a command line utility, and the experience really isn't as nice as, and I hate to say it, the Adobe product. The Adobe product has, Acrobat Pro has facilities for getting rid of all sorts of metadata and downsampling images. The interface for this is really nice. Executables, right? So binary programs on your computer. There is one tool for this, and it's called UPX. The reason you should use this is because executable files are really not known for their size efficiency, right? So on all platforms, really. The ELF format on Linux, the Mach-O format on Mac OS, especially the Windows exe format, right? You've got these huge swaths of null bytes and just insane required padding, and UPX is smart, and it knows about all those formats, and it can intelligently compress them. So the way that works is it wraps up your executable, and it changes the entry point of your binary to point to its own decompressor, right? So your new binary that you get out of it is a file where the entry point points to the UPX decompressor, which unpacks your real binary at runtime and then executes it. So this is an example where I am compressing a Go binary, and it's shaving 37% off the file size. All right, so that's just at the lowest compression level. That's at compression level 1. And you can go higher, but it takes a long time, and I'm not sure I'd recommend that. OK, collections of files. So what do I mean by collection of files, right? We might have things like a Git repository. Right? A Git repository is really just a database on the file system. And Git repositories can kind of get bloaty over time, especially when people on the project that are working with you, they like to commit big binary files. Yeah, so just kind of an example, I was talking with a friend of mine a while back, and he was having trouble cloning his Unity project from GitHub. He was like, man, you know, it's taking me 30 minutes to clone this from the Git remote. I was like, maybe he knows what he's doing, and surely this is just a weird bug, right? Nope, turns out he was committing every single binary file, every big giant asset to his Unity project for months, right? And so the solution to that problem is BFG Repo Cleaner. This is real easy to use. The point of this tool is to get rid of large junk files from a repo, and yeah, you just basically tell it what kind of stuff you want to purge. It will destructively rewrite your history, so be aware of that, but it will successfully eliminate big giant blobs from your Git repo. Docker images. Docker images are really just a collection of files, right? The reason we want to compress these things is because big Docker images take longer to deploy than smaller ones, right? Not to mention the bandwidth cost of downloading the big giant 1 gig image that you're deploying. So Docker history is your friend here, right? It's going to show you which commands introduce layers into your image. Spoilers, it's all of them. And it will show you what the size of those layers are. On the right-hand side, they're the size. So how do you trim down those layers, right? Docker base images kind of vary wildly in size, right? You can have Debian or CentOS image that are as big as like 200 megs, and that's even before you've added any of your own stuff to it, right? So definitely use a small base image. Alpine base image is 4 megs. You really can't beat that. Use fewer layers. When you do a bunch of run commands, you do run this, run that, run the other thing. Each one of those run commands is going to create another layer, right? So if you take a look at official Docker base images, the thing that they do is they combine run directives into one run, and that gives you one layer for multiple commands. Remove documentation. What are the odds that you're going to be looking at PDF or HTML documentation for your packages inside of the container, right? You don't need it, get rid of it. Remove manual pages. I don't know when I've ever run man inside of a Docker container before. So yeah, you can get rid of those too. Ooh, here's a good one. How many people here have heard of the GNU info documentation system? Okay, so like 1%. How many people here use the GNU info system on a regular basis? Yeah, so yeah, not a chance. Get rid of that stuff. It's not meant to be there. Okay, so final thing, purging your package manager cache, right? When you're downloading and installing packages onto your image, the archives for those packages are going to get buried away in a directory somewhere. and you don't need those, right? You just need the files that are dumped onto the disk. If you do happen to need these archives for whatever reason, you just download them again. Okay, so another type of collection of files, if you will, is a game update, right? So developers who put their games on the Steam platform have this massive benefit of being able to use Steam's infrastructure to download updates for their game, right? So when you're publishing a new version of your game, they have a smart uploader tool that does like a binary diff, and it will compare the old version of your game and the new version. It'll only make you upload the stuff that has changed. Same thing down the line when your users are downloading your game, it'll only make them download the stuff that has changed. Ideally, and so there's a game that came out a couple of years ago called The Witness, and the developer, Jonathan Blow, wrote a blog post about their attempts to try to be smart with optimizing the Steam binary diff algorithm. This is an exploration puzzle game, by the way. It takes inspiration from Myst. If you're into that type of thing, you should definitely check it out. So they have this build process where they're creating a big zip file, and they're trying to make the patch small and intelligent, and what they found was the way that their engine was saving those game files out, it was kind of causing the Steam binary diff algorithm to blow out their archive size, right? So by doing a simple thing, such as optimizing the order of the files in their zip archive, they were able to cut down the size of their update by 78%. And there's a blog post, so you can read all about it. Software updates, right? So not just game updates, but the example here that I want to give is Google Chrome. Right? The developers of Google Chrome, they're trying to figure out a faster way to push out silent automatic updates to their users. And what they did was they tested out some binary diff algorithms like BSDiff, and they found that it was okay. They were kind of unsatisfied with those results, so what they did was they implemented a custom patch system, which they call Courgette. I think I'm saying that right. The way that it works is it disassembles the Chrome binary and does a diff on the primitive disassembly of the executable. Right, so it sounds weird, but the point is that they're not doing a straight up diff between the compiled executables. They're doing a diff that allows them to kind of like internally rearrange pointers and do a bunch of smart math that lets them get much, much smaller file sizes on their updates. Okay, final thing I want to talk about is just generic compression algorithms, right? So these are things that you're using to create archives of files, right? So things like zip. Zip compression is pretty good with most things. It works everywhere. It works on Windows by default. It'll give you a generally acceptable level of file compression. gzip is kind of the same. It will perform at almost exactly the same level as zip. This is just the Unix, Linux version. Okay, so bzip gives you a little better compression at the cost of increased compressing time and decompressing memory, but it outperforms both of those things that we just talked about. And finally, xzip outperforms all of them. Here's kind of a comparison of what that looks like. So we've got zip and gzip up at the top there. They kind of overlap, so you can't really see them both. They're like identical lines there. And then, yeah, so the bzip algorithm is good, but xzip is what gets you that biggest savings there, right? Lower is better on this graph. That's all I got. Thanks. We've got a few minutes for questions. I know we went fast and we didn't cover everything, but I'd be happy to try to answer them.
Are you making this available? Because you had a lot of tools that, you know.
I can absolutely do that, yeah. I can, I'll put the slides up on the meetup page.
Outstanding presentation. Just a question in terms of where do you see the kind of theoretical relationship between compression ratios and then the amount of processing power, wherever it is, needed on the edge to compress and then decompress files or formats? Like, where do you see that going?
Absolutely. So in all of the generic compression things that we talked about there, the reason that those are so popular is because they don't break that ratio, right? There are definitely compressors out there, things like the PAC 8.0 compression algorithm that'll take hours and hours and hours to run. It'll give you way better file size than you could ever get from xzip even. But the point is that you don't want to spend that much time doing the compression. And yeah, absolutely, like on a mobile device, if you were deploying that type of archive to a mobile device, it would take you way longer to decompress it. Yeah, so there definitely is a significance to how long it takes you to both compress and decompress your stuff. You should try to find the things that will let you compress quickly and not spend, the point is, especially on mobile networks, right? If you're downloading some compressed thing to a mobile device, the threshold that you want to kind of try to target is for, does the amount of CPU time you're spending decompressing the thing beat the amount of time that it would take you to download a bigger version?
Some of those are asymmetric protocols, right? Like they can decompress much faster than they compress.
Sure, absolutely. Yeah.
I'd also like to add, I don't know if gzip and bzip can do this, but I know xzip can. It can spread the decompression and compression over multiple cores. So if you have a multi-core machine, you can actually tell it to use multiple cores. That will speed that process up as well.
Yeah, that's a good point. I don't remember when that was introduced, but I think it wasn't always there in xzip, if I'm not mistaken. It didn't always have parallelism.
With it, but LZMA, which was the first.
Okay. Yeah, so the point is, yeah, some compressors, decompressors can do things in parallel, which speeds it up both, yeah, decompression and compression side.
Any other questions? All right, let's give Tom one more round of applause.
Thanks, everyone.